Thanks. I'm excited to talk to you today about the economics of offline password cracking attacks. So this is joint work with Ben Harsha and Samson Joe, also at Purdue University. So this may be review for many of you, but let's first just define what an offline attack is. So here I am registering for an account at PlayStation.com. That's not my actual password, by the way. What's typically done is that the authentication server will pick a random value called assault. They'll append this random value to the password, and they'll apply some sort of cryptographic hash function to it, and they'll store the hash value on their server. Now, oftentimes, due to security vulnerabilities, attackers are able to break into this authentication server and steal all of these password hash files. So at this point, the attacker is only limited by the amount of resources that he's willing to invest trying to crack the password. Right? There's no way to lock the attacker out after a couple incorrect guesses. The attacker can try as many guesses as he wants. The only constraint is the resources that he's willing to invest trying to crack each password. So unfortunately, offline attacks are an increasingly common problem. Password breaches at major organizations have affected, at this point, billions of user accounts. So shown here is an incomplete list of organizations that have seen major password breaches. And I apologize to you if I left out your competitor's breach off of this list. So how do we mitigate the damages of such breaches? Well, one of the common tools that's used is called key stretching. And the basic idea is to make this underlying hash function a bit more expensive to compute so that a brute force attack becomes more expensive. There's a couple ways to do this. Hash algorithms like bcrypt or PBKDF2, they work by hash iteration. So instead of computing the hash of the password, you compute the hash of the hash of the hash of the password. And this increases the cost of computing this function. Now, there's a more modern way to do key stretching, which we'll come back to at the end of the talk, called memory hard functions, and SCRYPT, Argon2 ID are both examples of memory hard functions. All right, let's look back at our list of breaches. And in this talk, we're going to focus in on 4 of these breaches: Dropbox, AshleyMadison, Yahoo, and LastPass. One of the things that's notable about these breaches is that in each case, after the breach, we learned that each company was deploying some form of key stretching. So for example, LastPass was using PBKDF2 with SHA-256 and tau equals 100,000 hash iterations. So this actually exceeded NIST's minimal acceptable standard as defined in their 2017 guidelines, which basically set 10,000 hash iterations as the minimal acceptable level of key stretching. So after these breaches occurred, there were a lot of strong claims that were made. So for example, on the LastPass blog, they claimed that cracking our algorithms is extremely difficult, even for the strongest of computers. And after the Dropbox breach, it was claimed that the bcrypt hashing algorithm is very resilient to cracking, and frankly, all but the worst possible password choices are going to remain secure. So the key research question which we explore in this paper is, can we actually predict how many user passwords a rational attacker might crack after a breach occurs? So to do this, we extend a decision theoretic model, which was introduced at CSF in 2016. And we consider an untargeted rational password attacker. So by untargeted, I mean the attacker knows the password distribution. So he knows the distribution from which users select their passwords, but he doesn't have background information about the particular user. So he doesn't necessarily know your birth date or home address or other information that might help them to specifically target an individual user. We also assume that the attacker is rational, which means that the attacker is going to quit guessing as soon as marginal guessing costs exceed marginal rewards. So let's look first at marginal guessing costs. Marginal guessing costs are highly dependent on the particular key stretching algorithm that was deployed. So for example, with PBKDF2, we might ask how many hash iterations were used and what is the cost of the underlying hash function. So unfortunately, the cost of the underlying hash function, in this case SHA-256, has become pretty small. And in particular, to see why, we can look to the Bitcoin mining ecosystem. There have been a lot of application-specific integrated circuits that are tuned to just compute the SHA-256 hash function over and over and over again. In particular, this machine, the Antminer S9, computes this function 14 trillion times per second. That's what this 14 terahashes per second figure here means. And this machine is actually not prohibitively expensive. I just checked online yesterday, and the lowest price I could find was $1,200. Most stores sell for a bit more than that, but it's relatively affordable. So now the question is, can we actually estimate the cost of computing the SHA-256 function once? And we take an estimate from Bonnet and Schechter at USNIX 2014, which is based on the Bitcoin mining statistics. And they came up with an estimate that the cost to compute this function once is $7 times 10 to the minus 15, which means that the cost of computing PBKDF2 with 100,000 hash iterations is about 7 times 10 to the minus 10, or if you prefer, 70 cents per billion password guesses. So that figure is fairly low and is one of the significant pieces of our analysis. So the second piece of our analysis is to look at marginal rewards. So marginal rewards depend on, well, a couple things. First, the value of a cracked password. And to look for the value of a cracked password, we could look, for example, to black market sale prices. The marginal reward also depends on the distribution of user passwords. So in particular, we're interested in the probability that the next password guess that the attacker tries is actually correct. So here we assume that the password distribution is known, and PI denotes the probability of the ith most likely password. And finally, the third factor that can influence marginal rewards is diminishing marginal returns. So economics 101, if you increase supply, you decrease the price of a good. So in this case, if the supply is cracked passwords, as you crack more and more passwords, the value or price that you might receive from those cracked passwords on the black market starts to drop a bit. So let's take a quick look at the user password distribution. So to estimate the user password distribution, we use empirical data from Yahoo. In particular, we base our analysis largely on a data set of 70 million Yahoo passwords. And I want to stress that these 70 million passwords actually don't come from a password breach. These were collected by Bonnet back in 2012 with permission from Yahoo Legal. Later, we released this data set with differential privacy to protect users. Now, what you find if you look at this password data set is it actually fits a form of Zipf's law called CDF Zipf's law quite nicely. So in particular, if we look at the cumulative, the CDF, the probability of the t most likely passwords, and we plot lambda of t versus the rank t, we can see that on a log-log scale, this curve actually looks linear. So in particular, we have parameters y and r, where r describes the slope of this line in log-log scale. And this really characterizes the distribution of user passwords. So I'll mention that our finding here is consistent with previous findings of Wang et al., who looked at a number of prior breaches and found that all of these breaches were well modeled by Zipf's law. So we show that also the Yahoo distribution is well modeled by Zipf's law. OK, so let's suppose for now that the user distribution of passwords actually follows Zipf's law with parameters y, r, and let's suppose that the attacker encounters diminishing returns a. Now, what we can show is that there's a threshold which completely characterizes the attacker's behavior. So in particular, if the value to cost ratio exceeds this threshold, then the attacker should crack 100% of passwords. Right? In particular, if the value to cost ratio exceeds this threshold, then marginal guessing costs are always lower than marginal rewards. So in this case, v over k, v is the value of the password, k is the cost of the password. So intuitively, as the value increases, the attacker should crack more passwords. As the cost decreases, the attacker should crack more passwords. But we show that once you exceed this threshold, the attacker's best strategy is just to keep going until he's cracked all of the passwords. OK. So the formula for this threshold might look somewhat complicated. I threw it up here on the slide. The important thing to note is that it's just some function which can be computed given the parameters y, r, and a. So now let me show you what that looks like on a plot. Right. So in this case, we can compute the thresholds that we get for various password distributions. So the blue line here shows plots v versus tau for the Yahoo distribution. The red line shows the plot for the CSDN distribution. The black plot shows the RockU distribution. And the threshold really gives us our doom zone, right? So in particular, if the value and the so if our value v and our key stretching parameter tau lies within this red region, then this means that the rational attacker should crack 100% of passwords. So now it might seem a little bit odd for me to call this an optimistic picture. Why did I call this an optimistic picture? Well, we're making all of the best possible assumptions here. So we're assuming that the attacker encounters significant diminishing returns. We look at a wide range of estimates for the value of a cracked password based on black market prices. And we're actually considering the lowest possible estimate from any of these studies. And in all cases, we found that we lie squarely in this doom zone. So despite the fact that LastPass, for example, was using 100,000 hash iterations, which exceeded NIST minimum recommendations by 1 order of magnitude. OK. I should also point out here that we're taking the best possible threshold here. So we looked at several different password distributions. In this case, the doom zone shows the doom zone from the strongest possible distribution. So we're making all of the best possible assumptions, which should minimize the chance of password getting cracked, and still finding that actually the attacker should crack 100% of passwords. All right, so a quick grain of salt about the analysis on the last slide. So we showed that Zipf's law fits empirical data sets nicely. However, we can't be entirely certain about the shape of the tail of a password distribution. In particular, passwords that are observed once in a breached data set, we're not exactly sure what the true frequency of those passwords are. Another way to interpret this finding is that at minimum, the attacker will crack all passwords as long as the password distribution follows Zipf's law, and it's possible that a few of these passwords at the tail of the distribution are strong enough that they won't be cracked. So then the question is, how big is the tail of the distribution? It seems to be not too large. In particular, if you looked at the LinkedIn breach, it appears only 14% of the passwords there were unique. So I'll refer you to the paper. We have some model-independent analysis. So even if we make no assumptions like the password distribution follows Zipf's law, we can still argue that with high probability, the attacker cracks almost all the passwords. These bounds are derived using statistical tools and like Chernoff bounds. All right, so far everything I've told you is fairly bleak. Let me close by telling you something a little bit more optimistic. I mentioned that there's two ways to stretch passwords. There's hash iteration, and there's the more modern technique called memory hard functions. Intuitively, the way a memory hard function works is instead of just iterating a hash function, as soon as you start computation, you start filling memory with random blocks or random data that you've computed. And the idea now is that if the attacker is computing this function, he has to allocate tau blocks of memory for tau time steps. Right? So the nice thing is that now costs actually start to scale quadratically with your running time, right? Because the attacker has to run for time tau, but he also has to allocate tau blocks of memory to compute this function. By contrast, bcrypt and PBKDF2 cost actually scale linearly with tau. So quadratic scaling here is going to be a lot better. And there's a number of candidate memory hard functions. There's SCRYPT, which is Percival's proposal back in 2009. Argon2ID, which is a variant of the winner of the password hashing competition, and some new theoretical improvements to Argon2ID. So I claim that memory hard functions are incredibly helpful here. So if we perform a pessimistic analysis now, so if we assume that the value of the cracked password is $4 instead of 40 cents, so an order of magnitude higher, if we assume that there's no diminishing marginal returns, so the attacker's value for the next cracked password isn't diminishing as he cracks more and more passwords, even with these pessimistic analysis assumptions, we can still show that by using an MHF, you're actually predicting the fraction of cracked passwords down to 20%. Now, of course, you could do the same thing with something like PBKDF2, but that requires you to run for a very long time. So in particular, if you perform a ridiculous number of hash iterations, you can achieve the same effect, but now it's likely you're going to run for about 2 minutes trying to hash the password. And we believe that 2 minutes is most likely an unacceptable time from a usability standpoint. So executive summary of our findings, move away from PBKDF2 and bcrypt, move towards memory hard functions. Also for organizations, we'd recommend moving towards distributed password hashing. Pythia and Phoenix are examples of systems that do this. And for users, we would recommend enabling two-factor authentication and focusing more energy on selecting different passwords for different accounts as opposed to selecting more complex passwords. So with that, I will conclude and take any questions.
Peter Neumann, once again, I don't want to go into great detail, but you're over endowing Zipf. If you go back to my website, you'll find a paper by Witold Belewicz from the late 50s, where he showed you take any distribution whatsoever, you do the rank frequency inversion. Zipf law is the first order Taylor series truncation. Mandelbrot's law is the second order truncation, and it has the curve in it. And this explains the tail phenomenon in a lot of the cases. So you really want to look at that.
Sure.
Very simply, that's a remarkable paper, and it deserves people to understand it. And I did write a little bit on my website.
Okay, yeah, that's an interesting, interesting observation. I will stress, though, that a lot of the analysis does not depend on the assumption that passwords follow Zipf's law.
But they actually follow Mandelbrot's law.
Okay.
Okay, I'll take one more quick question.
Hey, Nicholas Allen from Amazon. Given the prevalence of password reuse, I was wondering if there really is much difference between different sites, and also kind of more forward-looking, if you did this iteratively, looking at cracking many different sites, does it change your analysis over cracking just a single site in terms of what amount of effort you'd put into the long tail?
That's a great question. I don't have a complete answer. The question is, when there's multiple breaches, how does the attacker trade off energy between cracking passwords in breach 1 or breach 2? How does the value of, how does the value change as a new breach comes out? These are excellent questions. I don't know that there's a complete answer in our paper, but certainly an interesting area for future research.
All right, thank you.
Okay, thank you again.